Ever wonder what the flight of a baseball has in common with the incredible graphics you see in 3D animation? Well, they both rely on this really powerful mathematical tool. And in this explainer, we're going to unlock the hidden world of parametric equations. Just look at this nautilus shell. It's this beautiful, intricate spiral. Now, if you tried to describe this shape with the simple y equals something with x equation, you'd have a really tough time. I mean, the curve literally overlaps itself and spirals inward. That's just a nightmare for standard functions. So that gets you thinking, right? How do we even begin to mathematically describe paths that do all this cool stuff? Looping, twisting, spiraling. And more than that, how do we capture the movement along the path? Turns out, the answer is to add a secret hidden ingredient into the mix. To pull this off, we need to introduce what you can think of as a hidden dimension. It's like an invisible controller that tells us exactly where we are on the path at any given moment. And this controller, this is what we call the parameter. So yeah, this secret ingredient is the parameter. The best way to think about it is like an invisible control dial. As you turn this dial, your position along a curve changes. We usually call this parameter t, and the most natural way to think about t is as time. Let's think about the Earth's orbit for a second. We all know it follows this elliptical path around the sun, but a basic equation for an ellipse can't tell you where the Earth is on, say, January 1st versus where it is on July 1st. That's exactly where our parameter t becomes a hero. If we let t be time, we can define not just the shape of the orbit, but our exact location on it at any moment. And this leads us right to the big idea of parametric equations. Instead of having just one equation that links x and y together, we have a pair of them. One equation tells us the x-coordinate based on time, t, and the other tells us the y-coordinate. So as t ticks forward, our xy point gets drawn across the screen, tracing out a curve. It's a really simple but incredibly powerful idea. Okay, so enough with the theory. Let's actually put this into practice. We're going to use this idea of time as a parameter to start drawing some shapes. I want you to picture this parameter t as like a remote control or a joystick for a single point on a screen. You just tell it the start time and the end time, and boom, the parametric equations just draw the whole path for you. Let's start with something easy, a straight line. Let's say our equations are x equals t minus 1 and y equals 2t plus 4. All we have to do is plug in different values for our time parameter t and see what coordinates pop out. So at time t equals -3, we're at the point -4, -2. At time t equals 0, we find ourselves at -1, 4. Simple as that. Now, when we plot all those points, we get a line segment. But, and this is the really cool part, look at the arrows. A parametric equation doesn't just give you the shape, it gives you the direction of travel as time moves forward. This is called the orientation of the curve, and it's something a standard equation just can't give you. All right, let's try something a little more fun, a parabola. This time, we'll let t go from -2 all the way to 3. And again, it's the same process. We just plug in values for t to get our x and y points. So if t is -2, we're at the point 1, -3. If t is 0, we're at -3, 1. And check it out, we get this beautiful piece of a parabola. But again, look at the orientation. We start down at the bottom, we sweep up and to the left, and then we curve back around to the right. A regular y equals f of x equation gives you the shape, sure, but it can't capture this specific dynamic journey along the path. That's the magic of the parameter. Okay, so you might be wondering, can we get back to our familiar x-y equations from these parametric ones? And the answer is yes, absolutely. It's a process called eliminating the parameter. So how do we get back to a regular xy equation? It's actually a pretty straightforward algebraic trick. First, you just pick one of the two equations and solve it for t. Then, you take that expression for t and you plug it into the other equation. After you clean it up a bit, you're left with a single equation that just has x and y. This reveals the underlying shape of the curve, but without all that extra information about direction and time. So far, everything we've drawn has been flat, 2D curves. But the real power of this whole idea, well, that gets unleashed when we take it one step further. Okay, this is where things get really cool. Think about it. A single parameter, t, acts like a single line of time, and we use it to draw a one-dimensional path, even if that path is twisting through 2D space. So, what happens if we add a second independent parameter? What could we possibly build with that? Well, here's the massive leap. With one parameter, t, you get a curve. But with two parameters, let's call them u and v, you can define a whole two-dimensional surface that lives in three-dimensional space. Now our x, y, and z coordinates all depend on both u and v. We've just gone from drawing lines to building entire worlds. So what can we make with this new power? Well, we can define all sorts of complex 3D shapes. How about a perfect sphere? The entire surface of this shape can be described perfectly with three simple equations, all controlled by just two little parameters. Okay, but how does that even work? How do two little parameters manage to create something so intricate? The absolute best way to think about it is weaving. Like making fabric. You have one set of threads going in one direction and another set going across them. You weave them together and you get a solid piece of cloth. We're going to do that exact same thing, but with curves, and these threads are called grid curves. Let's actually watch this happen by building a torus, a donut shape. First, we're going to hold one parameter still, let's say v, and we let the other parameter, u, do its thing. When we do that, we draw a whole family of circles. These are going to be the first set of threads in our weave. Next, we do the exact opposite. We hold u still and let v run its course. This gives us a second family of curves, all running perpendicular to the first set. These are the cross threads that are going to complete our surface. And when we weave these two sets of curves together, we get a complete, perfect, smooth surface. It's just an incredibly elegant way to build these amazing 3D objects from a simple grid of 1D lines. So let's just quickly recap the big ideas here. First, parameters add a hidden dimension to our shapes, something like time, which gives them a direction. Second, all you need is one parameter, t, to trace out any 1D path. And finally, and this is the mind-blowing part, with two parameters, u and v, you can actually weave those paths together to build entire 2D surfaces in 3D space. Now, this isn't just some abstract math concept. The characters in your favorite animated movie, the sleek body of a new car, the design of a futuristic building, all of it is designed and rendered using parametric surfaces. It is literally the language computers use to build our virtual worlds. So the real question is, now that you know the secret, what would you design?